we are going to be looking in detail at the diffraction pattern produced by a single slit. As with interference last week, we are aiming to be able to find at what angles you get bright and dark fringes. The diffraction pattern from a single slit is called the Fraunhofer diffraction pattern. To understand how it comes about, we have to abandon the assumption that we've made up till now that the slits can be treated as point sources of light. In other words, that they are almost infinitely narrow. In this lesson, we will see how the finite width of the slit is the basis for understanding Fraunhofer diffraction. So, just to clarify, diffraction is the general term for the behaviour of waves as they pass a narrow aperture or sharp edges of an object. A diffraction pattern is what we see on a screen that is placed in the path of the light leaving the aperture. And as we'll see, the bright and dark patches are caused by interference between light rays passing through different regions of the slit. We can explain Fraunhofer diffraction by examining waves coming from various portions of the slit as shown. So we have a slit here of width A, and we assume that the light reaching it is monochromatic, which means just one wavelength, and is coherent over the width of the slit, so that all of the waves reaching that slit are in phase with each other. They're at the same point on the wavefront. So, according to Huygens' principle, each portion of the slit acts as a point source of light waves. Hence, light from one part of the slit can interfere with light from another part, and the resulting intensity on a viewing screen depends on the angle theta. To analyse the diffraction pattern, we divide the slit into two halves. We assume that all rays are in phase as they leave the slit. First, we consider rays 1 and 3, 1 down at the bottom and 3 right in the middle of the slit. After leaving the slit, ray 1 travels further than ray 3 by an amount equal to half the slit width times sine of theta. This is very similar to double slit interference. The path difference between rays 2 and 4 is the same amount, and also the path difference between rays 3 and 5. If each path difference is half a wavelength, each pair of rays will cancel each other out, and there will be destructive interference. Therefore, all the waves from the top half of the slit interfere destructively with waves from the bottom half of the slit when A over 2 sine theta equals half a wavelength, or lambda over 2. So this simplifies down to sine theta equals lambda over A. And of course it can be plus or minus as the light spreads out both up and down. But we could also consider dividing the slit into 4 so that the path difference is A over 4 sine theta. That leads to sine theta equals plus or minus 2 lambda over A. And in the same way, we could mentally divide the slit into 6, and we could find destructive interference when sine theta equals plus or minus 3 lambda over A. Now all of this gets us to the general equation that if we have a slit of width A illuminated by light of wavelength lambda, there will be dark fringes at the angles sine theta equals m lambda over A, where m equals plus or minus an integer. Now, just knowing the positions of the dark fringes isn't yet telling us anything about the variation of light intensity along the screen. What we see, though, is that each bright fringe lies approximately halfway between the dark fringes, and the central bright maximum is about twice as wide as the secondary maxima. There is no central dark fringe, as shown by the fact that there is no m equals 0 in the dark fringe equation, because that would correspond to the theta equals 0 straight ahead.